variation of diagrammatic Monte Carlo is something that we recently cooked up at Rutgers, and the inventor is Kun Chen, who is in the audience over there. Yeah? So, I'm going to try to argue that we have now a systematic method to solve an electronic structure problem, hopefully, in not so distant future. Well, first I need to start with things that exist and people use for a long time successfully. There are approximations in material science that people are using, such as GW, but unfortunately they are not systematic. So first order perturbation theory is usually called GW, and it gives pretty reasonable gaps in semiconductors, but of course there are problems. While G0, W0 comes close to parameter gaps in semiconductors, we don't have error bars in the calculation. And moreover, it's well known that if we replace G0 by the self-consistent G, the gaps tends to be too large. Then if we do self-consistent, partially self-consistency and quasi-particle self-consistency, then the gaps tends to be slightly too big, but sometimes they are slightly too small, so it's not systematic. And what's even more important is that all these methods are not Baum-Cardano conserving. So the fully self-consistent GW it is, but all others are not Baum-Cardano conserving, which is a big problem because that means that they are not stationary and they're not robust to small perturbations. So for example, your implementation will always have sterilization errors, and this will always propagate in your final solution. So it's very important that we build conservation laws from the very onset in each step in Monte Carlo summation.
G0, W0 concern?
No.
Okay.
So the point is there is a need to go beyond that. Now, of course, there are dynamical mean field theory is very successful, and we know several extensions of dynamical mean field theory, but the controlled extensions are extremely expensive. So controlled expansions are either cellular DMFT by Gabe Kotler or DCA by Mark Gerald, who just passed away. So these are controlled approximations. Unfortunately, they're exponentially they scale exponentially with the system size. So if you have a very nice unit cell in a solid, then the cellular DMFT tends to be a very good way of calculating electronic structure for this. But of course, it's very hard to take into account the long-range Coulomb propulsion properly in such an approach. At least it's not clear how to do it. There are lots of diagrammatic extensions of dynamical mean field theory that appeared recently. Again, as far as I know, all of those are either not systematic or extremely hard to converge at high orders because they require more and more complicated vertices, 6-leg or 8-leg vertex. So we want to go a different route, and that's our algorithm that seems to work very well, at least in the Coulomb gas, was tested. So there are two pillars of this algorithm. So the first is variational principle to determine the best starting point for perturbative expansion. So I'm going to show you what type of variational principle we have in mind. It has to do with old work by Feynman and Kleinert. Then the second pillar is, of course, the diagrammatic Monte Carlo, but done in such a way that you will leverage sign blessing that was invented back by Prokofiev and Svistuno. The idea here is that to get this sign blessing work for us efficiently, we want to group lots of diagrams together and evaluate the entire group of diagrams together, not each diagram separately, because each diagram separately is very large, but there are lots of diagrams which are large and almost cancel each other. So we need to take into account the proper group, and we know what are the proper groups. Okay, so now first let me explain you this variational principle in a simple example that was given by Kleinert and Feynman, which is the harmonic oscillator. Okay, so just to understand what this variational principle is. So let's say we have a harmonic oscillator which has anharmonic oscillator which has the x to the 4 coupling here, coupling potential, and then we do weak coupling expansion for this perturbation, and we see that at small omega, all the terms, all the perturbative terms diverge. Okay, so for small omega, that's clearly a a bad expansion. But then the idea of Kleinert and Feynman is that we introduce variational parameter capital omega, and then add the counter term here. And when psi is equal to 1, of course, this potential is regional potential. Okay. So, but now we're going to expand with respect to psi to the n. So we're going to expand with respect to this new perturbation, and then we're going to perform power expansion just as before. And then the crucial point is here. We're going to use principle of minimal sensitivity. So we're going to look. We're going to see where the energy with or observable, in this case energy, has zero derivative with respect to this variational parameter. And then we're going to take this optimal parameter and we look at the power series. Okay. So now let's do this for the first order.
Excuse me. So
yeah.
Your statement with small omega seems a bit strange to me because it's an expansion in powers of g over omega cubed, apparently, right?
Yes.
So I would say the problem is rather that the expansion has zero convergence radius.
Yeah.
Right?
Yeah. So you plug in here omega and everything diverges. But so the point is you can turn this with this simple trick. You can turn this into a nice converging series that converges extremely fast. So that's the idea. Okay. So what did we do? Well, now we have the Hamiltonian is equal to H0, which has this capital omega in here, and then the perturbation is this. And we can calculate basically analytically the first order correction, which is thus the average value of the Hamiltonian in this ground state of the new at new frequency. And well, the value is this. Okay. And now we see that if we plug small omega to be 0, this is completely finite. It doesn't have any problem with divergency. And let's say that we're interested really in omega is equal to 0, where previous series was diverging. Then we can, well, first we need to apply principle of minimal sensitivity. We take the derivative of this expression with respect to capital omega. We get this equation, doesn't it? And then this is the solution. So we need to take capital omega that satisfies this cubic equation. Okay. Now we are mostly interested in small omega being 0. So then it's very easy to solve. We see that optimal omega is just 6g to the power 1/3. We plug this back into the expression for energy, which is here, and we get that that at optimum, the first order correction to the energy goes as g to the 1/3 times a constant, and we can calculate this exactly, and we see that it's almost identical. So the first order correction already gives you almost identical expression for the energy. Now this is not an accident. What they managed to calculate is this energy up to 40 digits by hand. So you can really see that this scales, each order gives you exponentially better accuracy. So and the interesting thing is that this series has an interesting dependence on this parameter capital omega. So if we take parameter capital omega too small, then each order tends to be more and more diverging. If you take this capital omega to be large, we see that each perturbation order produce more larger plateau of values where you can take the value, the optimal value. Okay, so therefore, when you go to higher orders, typically you need to take larger capital omegas, and there is a larger range of capital omegas that you can take, which gives you optimal value of your parameter. Okay, so that's useful because, well, we see the same thing in Coulomb gas. So there is a large region of frequencies of parameters that you can take where your answer is very good. Okay, so this is what we're going to use for screening in the Coulomb gas. Okay, so now what do? We split Lagrangian into something L0 that we can solve exactly, and then the perturbation. And now, how do we split this? So choose the good reference system L0, which allows for emergent properties. So we want to leverage the locality of correlations. We know that LDA, which has locality to a point in 3D space for correlations, and DMFT, which has locality to an ion in 3D space, are very good starting points. So we want to leverage this. So therefore, we're going to choose in L0 to deal with screen Coulomb propulsion rather than a long-range Coulomb propulsion to start with. But of course, we're going to add a counter term so that the entire L is exact. Then we optimize this delta L with principle of minimal sensitivity or a normalized condition. I will explain you this later or more precisely. Of course, this delta L will make L exact. And finally, we use Diagrammatic Monte Carlo to evaluate Feynman expansion to high enough order so that we see convergence. That's the idea. Okay, so again, this was done up to now only for electron gas. There is a plan to do it in real systems, but not yet done. So the electron gas it's the simplest possible system that that interacts with a longer Coulomb propulsion that can always be rewritten in terms of the interaction with bosonic field. So we have here bosonic field that has q squared divided by 8 pi dispersion. And well, what did we do? So this is identical Lagrangian that I wrote before for Coulomb gas. Now we are adding here screening lambda q, and we are subtracting here the same term. Okay, we're adding and subtracting, so that's the usual story if we do the counter terms. Then we add here some extra single particle potential, and we subtract it here as well. So we have two counter terms. One is for the interaction, and one is for the Green's function. Okay, so this counter term for the Green's function is the usual shift of alpha that we heard a lot about yesterday. What did we achieve then? So our Coulomb line is now screened statically, and it's short range. And at the same time, we have this counter term that we need to take into account order by order. And the Green's function propagator now needs to be decorated with this extra counter term. Okay, but the good thing is that of course we have freedom here to choose potential to be the optimal or the best potential that we can come up with. Now, what are the advantages of this approach? We don't need to deal with dynamic screening effects, which are somewhat painful to do in real systems. No need to deal with long-range Coulomb propulsion because I believe Mother Nature is local. This hopefully converges much better than if we start with full Coulomb, with long-range Coulomb propulsion. Screening lambda regularizes the weight of the Feynman diagrams.
It's only in the case if it's your personal matter.
Okay. So this screening lambda regularizes the weight of the Feynman diagrams at small q, and that actually it's very important because this makes Diagrammatic Monte Carlo more efficient. So it's also useful for numerics. Of course, we can start with the best single particle propagator if you want to. So this VK here can be either DFT constant potential, can also be DMFT self-energy, for example. So we can build on the best possible approximation for the solid that we have at hand. Okay, so what did we do practically from uniform electron gas? Of course, we didn't do DMFT, uniform electron gas. So we choose this VK to be screened Hartree-Fock at the first order. So this sigma exchange here is the screened Hartree-Fock, which screening is lambda, that's going to be optimized. And then at higher orders, we still had to add a little bit of counter term so that we work at constant density. You know, at each order, so the chemical potential will get changed, and then the G and G0 will not have the same physical Fermi surface. We want to have both G and G0 to keep the same physical Fermi surface. It turns out that in this case, the convergence is most uniform for all momenta. So therefore, we have to add this little counter term each order by order so that we fix the physical Fermi surface. So in solids, of course, there are better choices. For example, constant potential or LDA plus DMFT. The advantage of LDA plus DMFT here as a counter term is that we also have expansion of LDA plus DMFT self-energy in powers of n, and then we can subtract counter term much more efficiently, order by order. And in the Green's function, of course, the entire expression of LDA plus DMFT self-energy will enter. So that I think it's a very useful thing to explore in future. Now, how do we choose then the screening? I said that we're using this variational principle, isn't it? But there are other choices that we tested and eventually decided not to use them, and I will explain why. So one can roughly calculate the average perturbation order being trace lambda VQ, which is less than or approximately lambda divided by physical polarization at Q is equal to 0, omega is equal to 0. So if we choose that lambda is roughly minus polarization, at Q is equal to 0, omega is equal to 0, we see that the perturbation order is going to be close to 1. The average perturbation will be close to 1. So it means that we should get very rapid convergence. But unfortunately, this means that we have a horrible oscillations order by order. Okay? So we can't conclude anything by choosing small lambda. So now the other choice is we're actually adding here lambda to q square. So we see that if we add lambda to q square and choose lambda to be minus 8 pi times pi, then we see that we have exact cancellation between bubbles and this counter term. So in other words, this is equivalent to using lambda as self-consistent, like a self-consistent approximation. So let's say we do self-consistent GW. Okay. In this case, lambda divided by 8 pi is going to be very close to polarization at q is equal to 0, omega is equal to 0. Okay. Now by previous equation, we can immediately realize that this will lead to that the convergences should be achieved around perturbation order 25. Okay. So way too large perturbation order for our current capabilities. Okay, so the convergence is going to be probably very nice, but we need very, very high perturbation order. Okay, so at the end of the day, what we realized is that this variational principle is way better because convergence is achieved around order 5 or less, depending on RS, however, which is still 5 times faster than what you would get if you do it self-consistently. So therefore, this trick of allowing lambda to vary and optimize it was very useful. Okay, so now this is the perturbation theory that we are doing on a computer. Of course, I'm showing the first order, the 0th order, the first order, the second order, and so on. Notice that at the first order we have Coulomb interaction which is screened by lambda, but also we have the first order counter term which exactly cancel each other. Okay, so at the first order we're going to get the usual RPA. Okay, so the first order is usual RPA, and then we have higher and high orders. Okay, so now next, what do we do with the sign problem? So in order to achieve the sign blessing, we want to make sure that our weight in the Monte Carlo is not weight of each diagram separately, because usually when we do let's say classical diagrammatic Monte Carlo, we take the absolute value of each diagram, then we sum over diagrams, and then we integrate over all internal degrees of freedom, doesn't it? Now the trouble is that each diagram is very large, but diagrams mostly cancel. Okay, so the physical way that we actually need to calculate is the absolute value after we integrate over all diagrams, all topologies, and integrate over all internal variables. That's the weight that we actually need to calculate, doesn't it? So the point is that physical weight is usually way, way smaller than the weight that we use in Monte Carlo when we do the random walk. So our solution here is to use a weight where we pre-sum analytically the diagrams that largely cancel. Okay, so our weight now is the absolute value after you sum over all topologies of diagrams, and then the Monte Carlo has only sign problem because of the integration over internal variables. And this is not a hard side problem, actually, it's very weak. So the pre-summation over all possible topologies is absolutely crucial. Okay, so the important observation here, however, is that just naively summing over all diagrams will still not solve your problem. The important point is to optimize how you sum over all those diagrams, because there's lots of choices. For example, here we have momentum K1 and K2. K1 and K2, let's say we have two diagrams, and if we just flip the two momenta in the second diagram, this sum analytically should be the same as this, but numerically it's not, because the diagrams look different, doesn't it? So I'm just flipping these two variables here. I'm choosing different choice for my momentum summation in the second diagram, and well, the cancellation is not as good anymore. Okay, so therefore, how do you choose your variables in evaluating the Feynman diagram is crucial for good sign blessing. Okay.
This is specific to momentum representation, right? In position,
correct.
You don't care.
Correct. In position, this is easier. Yes, indeed. Mm-hmm. Yeah. So what I didn't explain is that we're using
one thing at a time.
Yeah. What I didn't explain is we are using momentum and time. Okay, because it turns out that momentum and time is very, let's say, the functions are very smooth, and the convergence is easy to achieve in uniform electron gas. Yes.
Okay, that's
yeah.
Later.
Mm-hmm. Okay. Now, so how do you combine diagrams? Okay, of course, it turns out we combined all the diagrams that contribute to the same order, but still, the important question is how do you choose internal variables to get good sign cancellation? Okay, so there are certain symmetries that we can use to do that. The first one is the crossing symmetry. So we know that when we exchange each pair of two fermionic propagators, the diagram changes just a little bit. So the only thing that changes is basically this wiggle line here. Some momentum on this momentum and frequency of this wiggle line changes. Everything else remains the same in the diagram, okay? And the sign changes. So that immediately tells you that the diagrams which differ only in one exchange of the fermionic lines will largely cancel. They will be almost identical with a little change of sign, with a change of sign. So therefore, these two diagrams can always be grouped together in something which people call Helmholtz diagrams. Okay? Now it turns out that this can be done even at a higher order. So whenever you exchange two fermionic propagators, you get similar cancellation. But at the lowest order, this is just rewriting Feynman expansion into Helmholtz expansion. That's the first step. Then the other step that we do is we are using basically word identity. In other words, we group all Feynman diagrams together which contribute to the same, which are shown in the Baim-Kadanow algorithm to be required for conservative approximation. Okay, so Baim and Kadanow derived this conservative approximation theory, doesn't it? And they introduced something like external potential, U12, and then they take derivative of log z with respect to this U potential to generate all possible diagrams that contribute either to the single particle or the two particle quantities. Okay, so there are several diagrams you can get, and it turns out that all those diagrams you have to combine. Okay, why? Because they largely cancel. It's the same story. So they largely cancel. And what's even more important, and now each Monte Carlo step in our approach is conserving. So it's not that you get conservation law after you sample for a long time, but each step in the computer is conserving group, according to Baim-Kadanow sense. And then the final step is that we have some counter terms and corresponding diagrams. For example, for counter terms for the interaction, always comes with a bubble diagram. And the bubble diagram and this counter term can always be combined together into a single object, and they also largely cancel with each other because they have the opposite sign. So this is also something that can help a lot with the sign problem. So now let me give you a concrete example at a third order, because that's usually the easiest way to understand things. The algorithm can proceed in the following way. So first we generate a Feynman diagram for log z, which is written in a Helmholtz type. Okay, so this is the 4-point vertex, and this is a 4-point vertex. Okay, so we have a log z Feynman diagram, and here in this log z Feynman diagram we choose momentum loops. Okay, so this is one momentum loop, this is the second momentum loop, and this is the third momentum loop. Okay, and now we're going to fix this momentum loops. In all Feynman diagrams that we generate from this, you will have exactly the same momentum loops, and actually they will have exactly the same Green's function propagators. Okay, so then in the second step, we take the second derivative with respect to u to get polarization, for example. So we attach external vertices here or here or here or here, or there are several choices, isn't it? These are all the polarization diagrams we're going to generate, and then we rewrite this. These are still Helmholtz diagrams in the sense that these points here are 4-point vertices, and now we can rewrite them in terms of usual Feynman diagrams that we are familiar with, doesn't it? And this generates lots of terms. I wrote here 4. This generates 6 Feynman diagrams. And now you can see that these momentum loops are identical here and here, identical. So basically, the product of fermionic Green's functions here and here are exactly the same, or actually in all of those diagrams, they're exactly the same. Okay. So the only difference is in the Coulomb lines. Coulomb lines have different momenta from one diagram to another, and the sign is different. Okay, so you see that these diagrams should cancel tremendously. Okay, so almost the final result out of those diagrams is almost nothing. Okay, so there is also a trick that actually it turns out that with this step you generate 2 to the n diagrams, because each interaction can be either going in this direction or you can switch it, doesn't it? So therefore, at order n, you generate 2 to the n diagrams in this way, and it turns out you can calculate all 2 to the n diagrams in the n time, not in 2 to the n time, but in n time. So you can save exponentially amount of computer time, because it turns out you can write all these diagrams in terms of the binary tree. Okay, and then evaluate the binary tree rather than actually the Feynman diagrams. That's a little trick which I don't have time to go into it, but if somebody is interested, we can discuss. Okay, so now we have an efficient way of calculating high-order Feynman diagrams, and so what we can compute. So this is spin susceptibility for RS is 4. This is pretty interacting system, pretty strongly interacting, well, moderately interacting system. And we see what happens. So now here I'm plotting spin susceptibility at Q and omega is equal to 0. Very sorry. So Q and omega is equal to 0 as a function of lambda. So this parameter that we want to optimize. And you can see at the first order, we don't have yet optimum. But then when you go to the second order, we clearly have an optimum. The third order, we have an optimum. Fourth, fifth, sixth, and so on. Order. At each order, we have an optimum. And if we take the value at this optimum, and you see higher orders have a larger plateau, just like what I showed at the beginning from the Kleinart's paper. So if we take the value in this plateau, and then we plot this as a function of perturbation order, we clearly see how nicely this converges. Okay? So this is where we do just bare perturbation theory, just like I explained before. There is a different way to do it. We can attach analytically the ladder diagrams on the left and on the right. So this is just pre-calculating the ladders, which is relatively easy to do, and then we attach them on both sides symmetrically. Then it turns out that this spin susceptibility that we're calculating converges even faster. So the first order is slightly too big. Then the second order doesn't do anything. The third order is here. The fourth order, fifth order, and so on. It's converged. And the important point is converges to the same value, of course. It has to. And this is the curve that we get. So it converges to the same value and maybe even somewhat faster. Okay. So now by looking at this convergence, we can estimate not just the error bar from statistics, but also the systematic error bars of the extrapolation. And here is the result of the spin susceptibility as a function of RS from 1 to 4. That's where we can really comfortably converge and give you the digits. And here are the values for the literature. Okay, so as far as I understand, our method beats everything that's available in the literature, at least for 1 or not even 2 significant digits. Okay, so our spin susceptibility has at least 1 or maybe 2 significant digits more than what you can get with any other method available in the literature. That's for the spin susceptibility. The charge susceptibility is slightly harder to beat, but nevertheless, what's important point here is that in this units, chi divided by NF, if you do RPA, you get that spin susceptibility is always 1. So we see that at RS is 4, RPA is 57% wrong for the spin susceptibility. For the charge susceptibility, it turns out RPA at RS is 4 is 220% wrong. So in other words, we have a 2.2 times wrong answer by doing just the RPA. So
can you get beyond 4? Because here it seems that you don't lose too much with
well, with the spin susceptibility, absolutely, we can go to 6 and 7. So spin susceptibility is fine. However, the charge has some very strange instability that we still don't fully understand. I will come to this. So we cannot do with the charge. So therefore, we didn't bother to do spin either. Okay, so we can calculate spin susceptibility as a function of Q, as a function, and also as a function of omega, but here I'm showing omega is equal to 0. So RS is 1, RS is 2, 3, 4, and 2 different ways of calculating it, and we see that basically they differ within the statistical error. The 2 methods give you the same result. Now, here is the charge response. I'm showing the dielectric constant, or actually 1 over dielectric constant, as a function of Q at omega is equal to 0. And these dots here are the previous diffusion Monte Carlo results. Diffusion Monte Carlo is state of the art in the field, okay? And it turns out that they always treat finite systems, so therefore they have just few points here, okay? Which lie pretty well on our curve. Of course, we have much higher resolution, since the curve is much more precise and smooth. But nevertheless, at RS is 1, this agrees very well with the known result. Then if we go to RSS2, there is also available results by diffusion Monte Carlo. Again, agrees pretty well. RPA is getting further and further away, of course. So this is RSS3. And then, look, RSS4, the available diffusion Monte Carlo results are pretty awful. Okay? So the scattering of those data is pretty bad. But variation diagrammatic Monte Carlo has no problem. So we can get a very, very nice curve even in RSS4. Okay? And we believe that this is very good estimation of the error bar, including systematic error, not just the statistical error. The statistical error is actually close to zero. This is very small temperature. It's 0.04 of the Fermi energy. Yeah, so now the problem here is that when you push RS to 5.24, which we tried, of course, we don't get convergence. And basically, every term grows, all the terms grow with the perturbation order. And so there is some charge instability that has not been properly explained after 90 years. So it turns out that even in diffusion Monte Carlo, it turns out that epsilon goes negative. So it goes negative for entire Q between 0 and 2kF. Okay, so there's clearly something going on. We don't know yet exactly what instability it is. We're still working on it, but there is something very strange going on at RSS 5.24. So if anybody worked on this and anybody had any ideas, please let me know because I'm very interested.
Oh, wait, this is strange that epsilon changes sign over a whole range of Q.
Yeah, yeah. Well, eventually at RS beyond 5.24. So you see the DMC results. I mean, we don't have these results. They're just DMC results. You look at the literature, it goes like that.
So the idea is that there should be a particular Q at which epsilon goes negative
first,
and then you...
Yes, then eventually you go beyond that, and then the whole thing doesn't make sense. But that means it probably has some other state. The state is actually not...
Sorry, what is the value of omega here?
Omega is 0. Sorry, I didn't write. Omega is equal to 0.
But you can get it also at 0.
Yeah. I'm just plotting omega is 0 because as a function of omega, it's a pretty boring curve. Omega 0 is the most interesting. Okay, so finally, what we are doing currently is along the lines that Kuhn was explaining yesterday. So this is another Kuhn's idea of basically calculating resumming the 4-point vertex to infinity. Because if we want to go closer to this instability, of any instability of the Fermi liquid, we want to resum the relevant part of the vertex function to infinity. That's the statement. So, well, there are several ways to do it, and Kuhn explained yesterday, but we are working with Dyson-Schwinger equation, which is an exact equation for the 4-point vertex, and it relates 4 points to a 6-point vertex. And the idea here is that we take from the 4-point vertex so-called relevant part, okay? And of course, to know what the relevant part is, you need to have some physical intuition. In this case, the relevant part would be the one where we take all the frequencies to 0, and we take the incoming momenta of the electrons to the Fermi level, okay? And everything else is relevant, okay? So for example, the Q, the momentum exchange, the momentum Q that the two electrons exchange is the relevant quantity that we want to keep, and then all the angles of how the electrons get scattered, this is also the relevant piece of the 4-point vertex. So we're going to keep this in R, okay? And then we're going to expand this gamma vertex in terms of R, and we are going to calculate some self-consistent equation to calculate R order by order in perturbation theory. Now, I'm not going to write this general expression that because Kuhn have done it yesterday. What I'm going to write here is the one loop calculation, the lowest order, the first order, okay? And the first order calculation actually resums all possible ladders in the particle-Hole channel, in the particle-particle channel, and the mixed channel. So basically, the result is very simple. It turns out that if we write this relevant part of the 4-point vertex, it has the direct term and it has the exchange term. And direct term, you can split into reducible part and irreducible part. The irreducible part is the one that contributes to polarization, while the reducible part is the one that can be written in terms of the 3-point vertex or in terms of W, which are all reducible. So then we have a self-consistent equation for a reducible part, and we have self-consistent equation for the irreducible part. So we can really split the two, and then we can calculate physical response functions by just using properly reducible and inducible parts in the lowest order Feynman diagrams. So these equations can be solved self-consistently, okay? And the question is, how good are they? Okay? And here is the result for the polarization at RS is 1. So the previous result that I was showing you for variation in Diagrammatic Monte Carlo with perturbation order 6, I'm comparing now with this first order Schwinger-Dyson equation. And you see that the RS is 1, we are basically getting almost identical curves, okay, with the first order correction, with the first order result. First order result is almost identical to the exact result at RS is 6, okay? But at RS is 4, we see that variation in Diagrammatic Monte Carlo still has some way. Well, we still have some way to go. So this is RPA. This is first order Schwinger-Dyson, and this is the variation in Diagrammatic Monte Carlo. So we still need probably second order, or maybe third order to converge. So the point is that with this Schwinger-Dyson equation, it seems that the convergence is way faster than using the usual regular perturbation theory. But of course, every order is way harder to do. I mean, they're much more complicated equations because we're resumming all possible loops, all possible diagrams that correspond to this, that contribute to the same loop order. Yeah.
Can you comment why at RS equal 1, RPA is so far away from the exact answer? If a red line is exact answer. Why RPA is so far away? RS is small.
Oh, this is well known. I mean, this is at RS is 1 for this is charge polarization. Charge polarization is, I think it's 20% wrong at RS is 1. Yeah. I mean, this is known from diffusion Monte Carlo. They have very precise value of this. 20%, yeah. 20% wrong, and here is 220% wrong. So factor of 2.2. Yeah, for polarization. Yeah, RPA is very bad. Yes.
I thought Schwinger-Dyson n equal 1 misses a line that is doubly crossed. So a diagram with a doubly crossed line. So how can it agree with n equals 6? I mean, I think it's order.
At RS is 1, these are extremely close. Now, which one does it miss? I mean, we can discuss this in private. I mean, there are these lowest order crossings, you see. This one exists, and this is the usual particle-particle ladder. This is the crossed ladder. And then we have all the particle holes in here, in these ladders. That comes out from one loop calculation.
Right, so if I may say,
yeah.
We're into the discussion period
yes,
now, which
exactly.
is great. But if there are other things you want to say, we should just...
Conclusions, so we can read this through, yeah. Mm-hmm.
All right, well then, let's thank Kristjan while we exercise.